Welcome to the last lecture of the first module of this course on advanced computer networking. Today, I want to discuss about a topic called as packet switching. In the last few lectures, what we saw is what is the routers in the networks are supposed to do. Basically, the lookup operation, and then we understood that packet classification and their quality of service and other things are the essential components of the routers in today's networks. What we'll do in today's lecture is to basically understand if I have to go about designing a switch, what exactly is there inside that switch. So here is the agenda. We'll spend some minutes in understanding the difference between the switching and the routing, the structure of the switch, and then there is something called as the blocking that happens inside the switch when you put it in, when you come up with the design. So what is that blocking, different types of the blockings, and then finally we'll venture into we'll take a look at the different types of the switch designs available in the market, or at least the strategies that are followed, and then we'll end the discussion on the something called buffering techniques. So the switching and the IP switching, whatever all, has a history in telecom networks. So basically, the switching operation that was happening in the IP networks is similar to that of what used to happen in the earlier days, the telecom networks. So, in the sense, the telephone network, the companies which provided the telephony services had something called as the exchanges. These are telephone exchanges, and here is a picture which actually shows such a telephone exchange. And back then, or in earlier days, the switching operation used to happen manually. Somebody is sitting at the these centers used to connect the people whom, for example, if A wants to talk to B, there is using patch panel cards. They used to connect the wires running from A to B in this board. So subsequently, such manual connection disappeared, and then they came up with mechanisms to do this operation automatically, where the exchange automatically finds out where exactly or who is talking to whom and how to establish the connection between those two points. So, using that as a motivation, the first routers or switches which were designed actually inherited the property, or at least the structure or the mechanisms that exist in the telephone switches. So, what we said is a switch. When I say the switch, the switch that operates in the IP network has got these components. One is the switch fabric, let me call it as SUP, and then initially you have got a series of input ports and then a series of the output ports. The packet arrive on these input ports, and then you need to forward those packets to the appropriate output port numbers. So that is what the switch, in a very brief, it has got. So switch fabric and some of the port numbers. So the line cards and other things that we talked are connecting to these port. So now the question is, how does the switch operate? What kind of using what technology the switch actually forwards the packets? How the packet is arriving on the input port number? This is what there is a picture which is showing the three things. One is the input. When the packet arrives at the input port, there is a processing happening. What is that processing? Basically, you need to stripe out the link layer header and then decrement the TTL value, and then consult the FIB and send it to the appropriate output port number. And the switch fabric is the one which is actually establishing the connection between the input port and the output port. And once the packet goes to the output port, there is some more processing happening. So that processing is basically you are adding a link layer header corresponding to the link that exists between this switch and the next hop switch. And switch control is the place where the logic or the how the FIV information is constructed. A bunch of routing algorithms run inside that control plane. So this is what we understood. So now the switches, when I say the switch, it's actually the router. This is a generic term that is used. Anything that is doing the routing and the switching, all of them, including the layer 2 switches, fundamentally using the same mechanism. So that's called as the switch. So you can very well call it as the router as well. So these routers are up to two types. One is which work completely using the optical fiber technology, where the input, the packet data is coming in the form of a light, it's a wave, and the output that exits from that router is also is in the form of a light, and it operates completely inside by processing that light information itself. It actually does the processing. So be it the consulting the FIV information or other things, whatever it is. So the two entry and exit are in the form of the light, and then the processing is actually done in the form of the digital data. Basically, you need to interpret that what packet, what data it is carrying, and the header information, and what is the IP address, and all that you interpret, and then you look at the FIV information. Based on that, you make the forwarding decisions. And there is a second category of the switch, which or the router, which actually receives the input or the packet data is arriving in the form of the light. It's an optical fiber on the left hand side, and it converts that data into, which is received in the form of light, into an electric signal, and then transfer it to the knob. So the entry is in the form of a light, and the exit is in the form of the electric signal. So these are the two kinds of the switches that you find. Most of the backbone networks in today's internet or the networks are basically completely the designed or working using the optical technology. Maybe the last mile connectivity and the some of the distribution switches might have this second category of the switches. So these are the two categories of the routers or the switches that you find in the net today. So after having understood this, how the data is actually getting transmitted, so let's try to motivate ourselves in order to look at what exactly is there in the switch inside, or the route inside, or how they are actually engineered, how the switch fabric look like. So let's define some of the terminologies, and after having understood those terminologies, we'll take a look at the different types of the switch designs or the fabric designs. So these are the following terminologies. So routing and the switching, what is the difference? So there are switches which actually work in the form of unicast forwarding and multicast forwarding. What do you mean by the throughput and the speed up, blocking and non-blocking, the output contention, and then the finally cell mode and the packet mode operation. So although when most of the discussion in this course is related to the packet mode operation, but nevertheless we did touch upon the ATM network, so we'll take a look at the cell mode operation as well. So we'll go one at a time. The terminology, we'll spend a minute in understanding each of these terminology in little more detail. So the first terminology, routing and the switching, fundamentally they mean the same thing. So routing and switching, what exactly is there inside a switch, be it the layer 2 switch or the layer 3 switch, or the be it the optical switch or the other type of the switch. So you have a mechanism to a FIB information is sitting on the line card, and there is a switch fabric, and you consult the FIB information, and the arriving packet, the header information of that packet is taken, and then you consult the information and forward it. So that is the so although you might have the layer 2 switch might have a different type of the information, but layer 3 switch might also have different kind of the information, but fundamentally the operation is to do the lookup, and you have a database, that is the FIV information in at the network layer or the IP layer, or the you at the layer 2 you might have the link layer addresses and so forth. You pick up the address from the packet, and then go and look into the database, and then do the forwarding operation. So that is the routing and the switching. So the more or less mean the same thing. The routers which are out there in today's networks operate in two modes. One is called as the unicast mode, and second one is called a multicast mode. So, although majority of the traffic that is going inside the network is unicast in nature, that is point to point, meaning a packet which is arriving on an input port wants to exit the router, and let me here is a picture. So, let me name these ports as 1, 2, 3 and 4, and if a packet arrives on the port number 1, and if it, after consulting the FIB information, if it has to be forwarded to the port number 4, all that you need to do is to establish the link between port number 1 and the 4. So, that is the job of the fast switch fabric that you have. Now, this kind of the operation is called a point to point, meaning you have one input port on which the packet is arriving, and the exit port number is also 1. So, there is 1-to-1 mapping. So, normally whenever we browse the content from the internet, it is actually a point to point information. Occasionally, you might also have a different kind of the traffic where you might want to transmit the arriving packet on a multiple port numbers. So, for example, if I have 3 input ports and then 4 output ports, 4 output ports, something like this, and a packet which is arriving on a port number 1. So, you may want to pass it on to the port number 4 or port number 5, and together are a subset of the port and output port numbers that you have on the switch or the router. So, why do we need to do this? There are some applications which actually demand such a kind of the operation. So, basically one packet is replicated and sent on two different output port numbers. So, think of this audio video conferencing application where a user, multiple number of the users are engaged in conversation, and you want to have all of them receive the content sent by all of them, then you may need to replicate the packets and send it on the multiple port numbers. So, how exactly it impacts the switch? So, basically the router or the switch need to be aware that such a so and so application is running, who is connected where, and on which port number I need to forward it. All that decisions you need to make right here. So, those are the operations which require the or of the type multicast type of the switches. And the next terminology is something called as a throughput and the speed up. So, throughput refers to the amount of the data, the aggregate amount of the data that is incoming, or the number of the packets or the bytes whatever are receiving, and how much of that is actually transmitted. So, in the best case, the whatever the data that is coming on your input port number. So, when I say the input port, all the input ports, all of them are able to you are able to transmit it. That is the best performance of the switch. So, by virtue of that, throughput is at the max is going to be 1. So, you might very well the switch might say that I am not able to handle these many number of the packets. Some of them might get dropped right there at the input port because of the non-availability of the space. The best case is everything that is coming to the input port is actually being transmitted to the output port, but otherwise a fraction of the what is coming to your input port is actually forwarded to the output port. So, that is called as the throughput. So, in a nutshell, so this number throughput is maximum has a ceiling of value 1. So, occasionally what might also happen that the switch fabric that is there inside your switch might be capable enough to transmit more number of the bytes or the bits that are arriving together inside to your input ports. So, let us say cumulatively I have maybe 10 Mbps of the data is arriving on the input port, and the switch fabric itself, when I say the 10 Mbps, that is per unit of the time. The switch fabric itself might be able to forward more than 10 Mbps of the data, although you cannot really forward more than what exactly is arriving on your input port, but it has got the capability to connect the input ports and quickly take that data and put it onto the output port. So if that happens, then we say that there is a speed up operation. So remember, what I am referring to is only to the ability of the switch fabric to take the content or the packets coming to the input port and putting it into the output port number. So only the operation of this switch fabric, nothing else. So that if it has got an ability more than what you have cumulatively able to receive on your input port number, so then we call it as the speed up. So technically you can have a speed up of more than 1.5 to whatever is the switch fabric is allowing you. By that factor you can actually speed up the operation. So we said that the switch actually has two components. One is the port connecting to the switch, and the second is the switch fabric. And the way switch fabric makes these decisions or establishes the connection is through something called as the connection processor. So there is a processor that's an intelligence that is built into the switch fabric, which knows how to establish a connection between one input port to the output port. So the connection processor itself are of the two types. One is called as the centralized processor, and this was the technology that was used in the telecom networks earlier age, where one entity is able to make the decision or how to establish the connection for every two port numbers, incoming and outgoing port numbers in the switch. And the second kind category is something called as the distributed processor. So when I say the processor, I mean to the intelligence built into the switch fabric on how to establish the connection between the two port numbers, nothing more than that. So the other operations which require some kind of processing are done at the input port and the output port. So the distributed switch processors are nowadays used in the IP networks. Whatever the switch that we use in the TCP/IP networks are more or less built with the distributed processing framework, and it is obvious to argue that centralized processing is actually good. It does not scale well. So only if at all you have to incorporate that kind of the processor, so you need to do that inside switches which are of the small scale switches. So meaning the number of the input ports and the output ports are less in number, and also you don't require the throughput and the scaling by many factors. So on the other hand, if you use the distributed processor, the scaling, you can add more number of the ports to the switch fabric, and then the many parallel connections can be established on the using those switch fabric. So because the intelligence itself is not placed in the one place, that does not act as a bottleneck for the processing. So as I said, when you make an establishment to connection establishment using the switch fabric from one input port to the one output port, there are different ways with which the connection establishment itself can be stalled. So here is a picture. Let's assume the switch fabric is here, and then there are some port numbers. Let me name them as 1, 2, 3, and 4, and 5, 6, 7, and 8 are the output port numbers. And one of the simplest way with which the packet the connection establishment can be stalled is, let's assume the 1 and 7 are connect with each other right now, and as we understood in our earlier discussion, there is a queue that is out there at the each input port, and the packets are placed inside this queue. So let me call this packets are P1, P2, P3, and P4. And let's assume at the time being the packet P1 is being transmitted on this switch fabric. The bits corresponding to the packet number 1 are flowing through this link, and they are going and sitting inside probably a buffer or the queue that exists at the output port. So now, remember every uh, input port also has got a queue. So there are some packets probably waiting at the port number 2 as well. So maybe those packets, let's call them are P10, P11, something like this. And what can happen is, because P1 is already getting transmitted on the switch fabric and the port number 1 and 7 are already connected, another packet waiting at the another input port number will not find a place or a pre-slot, because the switch fabric can connect the port number 7 to only one of the input port. So parallelly it cannot do the transmission. So such kind of the blocking is called as the output blocking, where there is a contention more than one packet arriving at the different port numbers wants to take an exit route to the same output port number. And if there is an ongoing conversation, so that blocking, because now the P10 has to wait, it has to go to the port number 7. That is what you have determined after consulting your FIV information. So that has to wait. So that kind of the blocking is called as the output blocking. And there is another kind of the blocking that might happen. So that blocking is called as internal blocking. So the way internal blocking occurs is, although the two port numbers, let's say in this figure, now the port number 1 and 7 are engaged in the exchange of the data, packet 1 is being transmitted. But to think of this case, so maybe the port number 3 on the queue corresponding to port number 3 has a packet. So let me call that packet as P10, and it wants to go to port number 5 and output port number 5. Because of the connection that is already established between the input port number 1 and 7, this connection, which has nothing to do with neither the input port or nor the output port, is now blocked for transmission. So if that happens, then that blocking is called as the internal blocking. So basically, two ports numbers I and j cannot be connected to each other when both are idle. So they are not involved or engaged in any kind of the data exchange or packet exchange. So if that happens, then we call it as the internal blocking. So internal blocking is a phenomenon of the switch fabric design itself, how it has been designed. So it's not able to transmit these packets or establish the connection between these two port numbers. So on the other hand, output blocking is basically because of the contention originating from the packets sitting at the head of the every input port number, so input port. So this contention output blocking, it need to be handled in some way. So there are some mechanism, it requires an arbitration. Who is going to, if let's say exactly at the same point of time, so along the time axis exactly, let's say at this time t, the packets on the input port number 1, 2 and 3, all of them are scheduled for transmission to the same output port. Now you need to determine, so the packets which are scheduled on the input port number 1, 2 and 3, no, they all of them simultaneously ask the switch fabric, I want to go into port number 7, I want to go to port number 7. Now you need a mechanism to determine who is going to get the slot, who is going to get the connection and able to transmit the packet to the port. So there are different ways of handling that kind of the blocking, and the mechanism that we use to do the handling or arbitration can impact the switch performance. So basically the throughput that you get out of that switch and the complexity of the switch design itself, and also it might also has implication on the cost. So these are the two main types of the blockings that you can find, and occasionally there is, we also talk about something called head up line blocking. So this happens because of IP packets are of the variable size, and a packet which is of the larger size might be getting transmitted on the switch fabric right now from one input port to the one output port. Because of that, a packet which is having or scheduled sometime later in the transmission might have to wait for a longer period of time. So that is called as head up line blocking, where somebody who is bigger in size is actually occupying the larger duration for the transmission and thereby blocking someone else who is behind the queue. So that, and although this has nothing to do with the switch design or the fabric design itself, but nevertheless that is also one kind of the blocking that can take place inside the switch or the router. So here is a picture which actually shows how the internal blocking might happen. So without worrying about the what type of the switch it is, so what you can think of is, on the left hand side there are some port numbers numbered from 1 to 9, and the output port numbers are also numbered from 1 to 9. So technically the input port and output port number can be same. So although we did differentiate them in our previous discussion, but they can be same as well. So what is shown along these lines, the thick blue color lines in this switch, is the current ongoing conversations, which port number is actually connected to which of the output port number. So you can see that 7 is connected to the port number 1 through the intermediate block here, and 8 is connected to the output port number 8, and the 4 is actually talking to the port number 5. So these are the 3 ongoing conversations. And now what you need to see it is, once I establish a link between or transmission between one block to another block. So let me call this block as A and this block as B and this block as C. So once I establish a connection between A and B, so for the block A there are 3 ports which are connected, and there are 3 incoming lines for the block B. When A and B are connected, so what it means is, only one of the input ports data or the packet being transmitted through that link to the block B. So maybe I might transmit the data from the port number 9 to using this link to the block B. So that is what it means. So if that happens, what it means is, I can transmit, I may not be able to transmit more than one input port numbers from one block to the another block. So you're looking at the parallel conversations that are happening right now. So 8 is connected to the output port number 8, 4 is connected to 5, and 7 is connected to 1. So if let's say the port number 9 wants to talk to someone, maybe port number 4 or 5, so that cannot be done, because so the output, the block A is engaged in the conversation. So the connection can go only through either of this block B or through this block. So those two are actually blocked now. So 9 will probably will not be able to transmit the data from whatever the packet we want to transmit to the port number 4, we may not be able to establish the connection. So this is an example of the internal blocking. So it is apparent that there are many other possibilities which can have the such internal blocking. So so that's the difference. So internal blocking is because of the constraint of the switch design itself, something is actually blocked, and output blocking is because of the contention that originate from the packets which are actually scheduled for transmission on the same output port number.